October 16, 2024. 1709 Universal Time Coordinated. 3 developers at Radiant Capital opened Safe Wallet to approve a routine transaction, a lending cap update they had signed almost every week. Each of them reads the screen. Each of them confirms on a hardware wallet. The devices light up, beep, and return valid signatures. Nothing looks wrong. Nothing feels wrong. $50 million is gone. The transaction the signers saw on their screens, and the call data their hardware wallets actually signed, were 2 different things. Four months later, a related attack returned, 30 times larger. February 21, 2025. Bybit, one of the world's largest exchanges, lost around $1.5 billion. Both incidents share a category, not a mechanism. What the signer sees and what the chain executes are not the same thing. Display execution divergence, as ZKSC founder Kazuki Kaneshiro calls it. The FBI referred to the Bybit actor as Trader, a group that industry reporting and security vendors commonly associate with the broader Lazarus ecosystem. This is not a story about careless teams. It is a story about a structural gap in how Web3 makes high-value decisions. To understand the pattern, start with the timeline, because the Radiant attack didn't begin in October. It began 5 weeks earlier. September 11, 2024. A Radiant developer receives a Telegram message from someone posing as a former collaborator. Attached, a zip file containing what looks like a project report. The developer opens it. The attackers now have a foothold. October 2nd. The attackers deploy a malicious contract on Arbitrum and BSC. Then they do something interesting, nothing. The contract sits dormant for 14 days. Block explorers index new contracts constantly, but Radiant's own monitoring did not turn that dormant deployment into an actionable, signer-level warning. October 16th. A developer proposes a legitimate cap update. The signing process fails a few times, flaky connections, nonce mismatches, retries. For anyone who has used a hardware wallet, this is a normal Tuesday. And that normalcy is exactly what the attack hides behind. At 17:09 and 18 seconds Universal Time Coordinated, a swap transaction executes, transferOwnership. Control of the pool provider moves to the contract deployed 14 days earlier. An automatic pause triggers about 17 seconds later, but that pause was never designed to block ownership transfers or implementation upgrades. It could not stop what had already executed. The FBI and Mandiant attributed the Radiant attack to UNC 4736, a cluster tied to North Korea's Lazarus ecosystem. The Bybit attack was more sophisticated, because this time, the attackers didn't target the victim at all. February 4, 2025. A Safe Wallet developer's Mac is compromised through a Docker container. The attackers weren't after that developer's keys. They were after Safe Wallet's infrastructure, the web application that thousands of teams trust to display their transactions. Around February 19, forensics teams later found evidence of a rehearsal. A dry run, validated before going live. Roughly the way a large enterprise validates a change before deployment. February 21st. As Bybit begins a scheduled cold wallet transfer, the JavaScript served from Safe Storage bucket has been modified. The malicious code activates only for Bybit's address. Millions of other Safe users see nothing. This was a targeted strike, not a broad net. On the signer screens, a normal transfer, Operation Type 0, a standard call. In the actual call data, Operation Type 1, a delegate call to an attacker-controlled contract. The Safe proxy's master copy is overwritten. The cold wallet now belongs to the attacker. $1.5 billion in ETH and staked ETH flows out. Within 2 minutes, the malicious JavaScript is deleted from the server. The FBI referred to the actor as Trader, a group commonly associated with the Lazarus ecosystem in industry reporting. And here is the uncomfortable part. In its public materials, Bybit referenced ISO 27001 and PCI DSS Level 1 certification. This was not a negligent organization. The failure was that one assumption, the signing interface itself can be compromised, existed in almost no one's threat model. So where were the security tools? The honest answer is, they existed, and some of them worked. Pre-transaction screening, real-time threat detection, post-incident tracing, this tooling is real, and the vendors behind it are credible. The failure happens one step later. Alerts fire. Signers don't read them. Kaneshiro spent 13 years building fraud detection for financial institutions, and describes the pattern bluntly. The system throws 100 alerts. Humans read 3. In one credit card fraud system he built, the model caught 80% of all fraud, a genuinely good result. But of every 100 alerts an operator saw, only 4 were real. 3 months in, operators had stopped opening alerts entirely. They had learned rationally that alerts are almost always noise. Why does every detection system drift this way? Because the incentives are one-directional. Miss a fraud, and there's an audit, a named owner, a loss on the books. Generate a false positive, and the cost, operator hours, attention, trust, appears on no balance sheet. So rules accumulate, just in case, until the signal drowns. An alert channel full of false positives doesn't get fixed. It gets ignored. The second mistake is simpler and older. Radiant's signers and Bybit's signers were making $50 million and billion-dollar decisions from a single source of information, one screen. Traditional finance would not recognize this design. When a bank moves a large wire, it confirms through multiple independent channels: the screen, a phone call to the counterparty, an email approval trail, sometimes physical paperwork. Not because banks distrust their people, but because the design assumes no single channel deserves 100% trust. If the screen is manipulated, the phone call catches it. That philosophy was built over 50 years of real losses. Web3 Multi-Sig copied the surface of this idea. 3 of 11. 5 of 7. The numbers look rigorous. But Multi-Sig requires multiple keys. It does not require multiple independent sources of information. If all the signers are reading the same poisoned interface, the threshold is arithmetic, not security. Two structural mistakes suggest two structural answers. First, explanations, not alarms. Psychologists call it the cocktail party effect. In a noisy room, you don't hear volume, you hear meaning. Your own name cuts through. Risk level high flashing in red is volume. A signer's brain has already filed it as noise. But a specific sentence is meaning. This transaction looks like a supply cap update, but it actually transfers ownership to an unverified contract deployed 14 days ago. Would one line like that have stopped the third Radiant signer? Nobody can prove it. But it's the kind of signal a human actually engages with, and it's the only serious answer to alert fatigue anyone has found. Second, an independent observation channel. Just as a bank verifies a wire outside the originating screen, a high-value Web3 signature needs a second look from a system that does not share infrastructure with the working interface. If one channel is poisoned, an independent one can still catch the divergence. Not a kill switch. A second pair of eyes by design. This is the thesis behind ZKSC and its product, Ninja. Run a verification layer alongside the working interface, not inside it. Cross-check who the counterparty contract actually is against a database of 90 million EVM contracts. Deterministically analyze what the call data actually does. Then translate both into plain language a human can read before signing. To be clear about the limits, no tool catches every attack, and no vendor should claim otherwise. The claim is narrower. 50 years of financial industry experience says independent channels and human-readable explanations measurably reduce the odds that a poisoned screen becomes a 9-figure loss. Web2 finance learned that over 5 decades. Web3 is trying to compress the same curriculum into 15 years. Radiant and Bybit were signed away by people doing their jobs correctly. So ask one question: when your next transaction is approved, how many independent sources confirmed it? If the answer is 1, you know the failure mode.